So welcome to DV Club. This is our last one of the year, and today we're focused on the auto generation of verification infrastructure for both IP up to SOC level. We have 116 registrations today, representing 72 companies in 24 different countries. Everyone is online as well. We're still doing everything on remotely for DV Club at the moment. And here's our agenda. We've had a last-minute change to the speaker from Agnisys due to an illness. So Nikita Gulliya, who's a project engineer, will be speaking first. And then Simon Davidman from infra. And finally, I will just give you an overview of some of the automation work we're doing at TESOL. It involves both AI and automation. We will finish at 1 o'clock. Yes, UK time, GMT, and we'll keep the time as usual. Okay. A quick thank you to our sponsors and our venues. At the moment, we're not actually physically running any venues, but ARM and ST support that when we go back to venues. Our sponsors: Agnisys, Brecker, Cadence, Synopsys, Impress, and TESOL. Okay, so thank you, and we'll move to our first speaker, Nikita, please.
Yes. Hello, everyone. I'll be presenting on the topic auto-generation of verification infrastructure for IP SOC. So let us start with the study from the Wilson Research Group, which says that most development time spent in verification is about 60 to 70%, and about 76% of the projects have 2 or more respins. And the main cause and the greatest verification challenge behind these respins are by far creating sufficient number of tests for verification of the designs. Now, there are multiple verification challenges which we pose, which includes high cost and difficulty due to lack of experience, resources, and a lot of manual work. Apart from that, horizontal and vertical reuse, which includes forwarding all the code to the firmware team, and they have their own different environment and language and focus. And vertical reuse includes reusing the same set of test sequences, register specification created at the subsystem or system level, which can have changes such as change in bus protocol or differences in configuration. Now, the solution to all those challenges is to have an auto generation of verification infrastructure. Now, suppose you've automatically generated the output from a specification. How do you do that? So the first step is to have single golden executable specification. Listed here are different kinds of specification which can be used for capturing the data. The register specification can be captured in system RDL or IP exact formats, which are industry standards. Apart from that, sequence specification can be captured in PSS format. The design specification, the application logic side, which includes FSM, data paths, non-addressable registers, they can also be captured in a template-based approach, which is discussed in the further slides. Apart from that, connectivity specification, where all the top level blocks, how they're interconnected, can also be captured and then output where various verification collaterals can be generated. Now they can be captured using Tickle APIs, Excel format, and many others. Register specification automation. Now, once the register specification has been captured, then you can automatically generate UVM RAL model. But what next? So here goes the cycle. So creating a UVM-based verification environment if it does not exist already, and then integrating the UVM model in it, then creating formal properties for the generated RTL for formal verification, Apart from that, writing sequences for register accesses, special registers, functional tests, C++ tests, making makefile for simulation, and then running simulation and collection of merged code and review coverage. Now, if the coverage is not 100%, go to step 3, again repeat, or add it to a waiver list. Now again check for the same process. Now if the desired coverage is achieved, then you're done with the verification. But if it is not received, then you again need to write sequences for various software register access, special registers such as alias, interrupt counters, functional tests, and C++ tests. Now, to avoid all the manual work, there are tool and provision where automatically outputs can be generated. Now, automatically register model can be generated for the DUT, and which will include the register focused cover groups as well. Positive, reset, negative test sequences will be generated for all types of special registers and software accesses. Apart from that, entire UVM verification environment, which gets you close to 100% coverage, will be automatically generated. Apart from that, SV properties, an assertion for register access policies and which are compliant to the bus protocols can also be generated, along with the makefile and tickle command scripts. And also some standard sequences for the registers can also be generated automatically. Custom test sequences and user checker events can be generated, and a makefile for various simulators can be generated. So more features and capability includes it is a push button verification, and it is compliant to standard bus protocols such as the entire AMBER family, such as AXI Full, AXI Lite, AHB, APB. It gives out of the box 100% coverage and automatic test sequences for all the special register and accesses, automatic assertion, make files for Cadence, Helium, Interquesta, LDEC, Grapefruit Pro, and also provides features such as auto mirroring, and it automatically generates about 30% of the verification code automatically. Now, in this snippet shows the verification environment generated automatically. We are targeting bus layer, register IP, and hardware application layer here. In automatic IP verification, we generate a verification environment from a golden specification and verify it using the inbuilt register sequence and custom sequences. So first, the IP verification environment hooks up to the RTL and IDS wrapper. Here the boxes represent the orange, gray and light gray components, which are automatically generated by IDS. And blue ones are user RTL. Dotted line represent the SV transaction for event capturing at the checker. And the reg bus agent is a component that converts register level transaction to bus level transaction and vice versa. So the tool generates reg bus agents for all ARM buses. A top level wrapper is generated, which contains instances of the register block and user application logic. And also there is one more component, which is called a tapper interface that taps the hardware interface pins as shown in the diagram. Model updater updates the RAL model via tapper interface wherever the RTL is updated and using hardware pins. The checker is one of the essential features which enables user to generate custom checks from a single specification. It automatically translates the checker specification to system verilog assertion code. Now, moving forward to automatic assertion generation. So what type of assertions are generated? They are based on different RTL behavior. And assertions can be generated for different register accesses, RTL interfaces, special registers, and IDS associated UDP, which means there are some functionality which is available in the tool specific to those. Apart from that, clock domain crossing, functional safety, such as parity, CRC, SecDec. And there are some system level assertions which are automatically generated as well. which includes assertions to check RTL ports connections, topology assertion, multi-master design assertions. Here you can see this is the slave bus interface, and these are all the set of registers and assertion which checks both read and write transfer. This diagram shows diagram shows the RTL, and this is generated by the tool automatically based on the register specification, and this is the application logic at the user side, and how at different level the assertion is being generated. Assertion is being generated right from the register bus stage, which is coming from the software side, and then the decode logic. There also assertion is being generated where all the internal registers reside, and the read back marks for reading the data back. Apart from that, there are some external components as well, the register which is kept external, and the read and write from the hardware side as well. The assertion is being generated automatically. Design and connection specification automation. So this is how a typical SoC looks like. This is the CPU, and with the help of an interconnect fabric, multiple programmable slaves are connected, and with the help of a bridge, there are some more peripheral slaves which are connected with the bus, and it contains different registers in it. For which specification can be written, and this is the input system RDL file. This is a simple, say, a block and have multiple register and fields under it. And this snippet shows the generated RTL for input system RDL and based on the formal verification. The output is in terms of properties and end property. You can check. And based on the software accesses and the bus protocol which has been used. This is the connectivity specification, which is connecting one target device to an initiator. The connectivity specification for connecting pin-to-pin connection, and this is this snippet shows the formal output which has been generated based on the RTL ports. Moving on to user application logic connected to register map. For an IP which are automatically generated from the register specification, which can be in system RDL, IP exact, or any format. And this is the user application logic, which needs to be created manually. The user application logic basically consists of a state machine and assigns with combinatorial logic, signals, input, output, sequential elements, data paths. So there is a provision by which all this information can also be captured with the help of a template-based approach. After capturing the entire specification, the register specification plus the user application logic as well in the specification, UVM prediction model can be automatically generated. UVM test sequences for complete coverage can be generated. Other collaterals are also possible, such as deadlock detection and documentation output. In addition to that, the entire RTL and System C model can also be generated from that golden specification. AI can also be used in verification here. The automatic tests which are generated uses a technique which is DRL, the deep reinforcement learning, with the help of which automatic tests are generated for achieving the goal. Now let us look at that with the help of one example of, you can see So with the help of the tool, this is AI-based generated UVM-based test. And this is the coverage results which is generated from it. It gives about 77.59% of coverage automatically, and it can be obviously increased by rearranging all the tests. Moving on to sequence specification automation. Now, what is verification and what is validation, what is the difference between the both? As you know, that verification is a process of testing the functional correctness against a given specification, and it includes terms such as functional coverage and cover points, constraint, and randomization. It includes simulation along with formal emulation prototyping, and its environment is typically based out of SV and UVM. On the other hand, a validation is based on a chip which is tested for all functionality correctness in a lab setup. And the environment here is bare metal environment with emulation of real processor and IPs. Software test, mainly C tests, which include automated C tests and custom C tests. So here, first the specification and architecture, microarchitecture exist in a design cycle, and then the RTL design, and from the specification, the RTL design is made, and then the next step is physical design, and the tape out takes place in a typical chip design and development life cycle, and then back from fabrication, the chip is tested. The verification takes place and the validation takes place, but validation takes up a lot of time in the chip design and development cycle before the volume shipment. So here Agnisys has a solution for that too, with the help of which you can have test for the higher system level environment. So with the validation model of the register and memory specification, there can be output in the form of C, C++ API and C, C++ based tests and user sequences. And there is also a RISC-V based validation environment as well. It also extends beyond register and memories to generate verification environment and user-defined functional test to verify functional behavior. And it also enables user to describe programming and test sequences of a design and automatically generate sequences ready to use, from an early design and verification stage to post-silicon validation. This is the bare metal verification. The bare metal environment includes not only the IPs, but also the CPU in the simulation. Now, bare metal programming means writing an application directly on the hardware without using an external application programming interface or any operating system, which means writing on to the CPU directly. So the tests are written in C language and are compiled and run on the CPU. So what we generate is a system level UVM-C mixed verification environment, and which is built around RISC-V VEED core. An automatic C-based test for register layer are generated. The C tests are synced with the UVM tests. And you can also have custom C UVM tests as well. So here you can see the CPU, and this side is the C test or the assembly cross compiler, and this side is the IPs and the UVM test side, and the C test and the UVM test are synced. This diagram illustrates how coverage is sampled in a bare metal verification environment. So in a bare metal verification environment, automatically generated tests are present for all types of register in a specification which are built using the compiler provided by RISC-V and converted into bus transaction. The bus transaction gets captured by monitor using the bus interface, which in turn updates the RAL model containing the coverage via bus to reg adapter. Challenges and development teams faced with sequences. Now, sequences are not clear or well documented, and their definition and interpretation are sometimes incorrect and inconsistent. And usually the register specification are written in industry standards such as IP-exact or system RDL RALPH. Or sequences are everywhere, like the architecture designers plan them, and then design engineer encode Verilog functionality, and verification engineer write them in UVM or PSS after interpreting the specification. Now, to solve all the sequence challenges, which includes not clear specified register specification or the RTL code and inconsistency, there's a tool with which you can generate custom sequences and capture them in a specification form. Now, the register data can be in any of these formats: IP-exact or system RDL, ROLF, XML, Word, Excel, OpenOffice, or Agnisys, GUI, IDS, NG. And then a custom sequence editor is present in Python API format or Excel format. Apart from that, sequences can also be captured in a standard way. The PSS, portable sequence specification, can be written. And from this, various outputs can be generated. For those once sequence specification, the UVM SV based file, the SV for validation, C sequences or automatic test equipment or firmware sequences, or MATLAB output, HTML platform, a flowchart type output cannot automatically be generated. Talking more about the PSS support. So PSS 2.0 is a new industry standard created by Accelera. Agnisys has been a member and contributed to it. We've already been doing the sequence part in other formats such as Excel and Python, and added PSS support to it. So we are an expert in creating the realization layer, which is the widest, most comprehensive register memory definition. And we do generate the C functions and UVM sequences from that. The benefit is to having one single golden source for register and sequences, which reduces time to market and improves quality. A possible output from the PSS file. Now this shows the PSS files, but first the register specification, which can come in from any of the formats which I've mentioned before, including these. And the sequence specification can be written in PSS files, and then using the Agnisys PSS compiler, all these collaterals can be generated. In model, the RTL registers can be generated, the UVM RAL can be generated. Apart from that, C++ headers can be generated. There can be output generated from HTML PDF form. Flowchart view of sequences can also be generated. In terms of run environment, verification SV UVM based environment can be generated for that, and validation C++ based environment can be generated. Tests, automatic register tests are present, standard tests are present, UVM based PSS tests can be generated. Apart from that, automatic register tests, C based PSS test can also be generated. From the PSS sequences, and apart from that, some miscellaneous output such as custom output, velocity based template, and some make files. So in conclusion, I would say that auto generation of 50-60% of verification collateral is possible today. And this number will only grow with specification, automation, and AI. For more, you can contact www.agnisys.com for more details. Thank you.
Okay, thank you very much, Nikita. It was very informative. So we have a few questions. We've got 5 minutes for a few questions. So where do you see, your last sentence there is quite interesting, this number only grew with specification, automation, and AI. Where do you see AI being applied, would you say, in this flow? What are the potential applications for AI?
Yeah, so currently on AI, we've been able to generate various test sequences. So where the most of the time and most of the respins of the industry takes place. So currently we've been enforced learning, DRL learning, with the help of which automatic tests are being generated, and then we are achieving close to 77% or about 80% of the coverage using AI. So this has been automated till now, but AI is been growing, and there are many more things which can be automated in the future.
Okay, another couple of questions. I think in the in your talk you mentioned IDS. Can you just say what IDS stands for?
Yeah. So iDesign Spec is a tool by Agnisys where you can write all these specification I've been talking about, whether it's been the register specification, sequence specification, connectivity specification, and then you can generate multiple collaterals from that, such as the RTL model, UVM, C, and all the environments and all. So this is to basically avoid all the manual work.
In IDS, and IDS stands for?
IDS is the full form is iDesign Spec. It is basically the name of the tool.
Okay, it stands for iDesign Spec, yeah?
Yeah.
Okay. Okay, and there was one question in terms of how does the IDS, if you're using IDS validate, how does that relate to any specific requirements? And the flow didn't show the requirements. So what you validated against in the IDS, please.
So IDS validate basically works at the sequences or the outputs or the tests which are generated. So through IDS validate, you can use those sequences at the SOC level, the higher sequence level. And also a bare metal environment, as I mentioned, around the RISC, a 5V core is also generated with the help of IDS validate. And with the help of PSS, which is Accelera, PSS 2.0, which has recently been released, a user can write their sequence specification in PSS, and with the help of IDS validate all the various sequence specification, whether it is in C, whether it is in UVM or SV, can be generated.
Okay. Thank you very much, Nikita, and thank you for standing in at the last moment as well. Much appreciated. Thank you very much. Thank you.
Thank you.